In section 6.3, we're looking at special factoring. Our objectives are to factor a difference of squares, factor a perfect square trinomial, factor a difference of cubes, and factor a sum of cubes. A difference of squares, you'll see, is in the form of x squared minus y squared. In this case, our factors are x plus y and x minus y. Let's do the example here. The first thing you want to do when you're doing any factoring is to factor out a common term, any greatest common factor. The greatest common factor is, in this case, 2. So we're going to factor a 2 out of the first term, dividing out a 2 from 2n squared, and that leaves us with n squared. And then we divide out a 2 from minus 50 to get minus 25. Now additionally, we want to factor this term, the binomial that we have inside. And you can think of n squared minus 25 as a binomial, but we can also think of it as a trinomial where the middle term is 0, n. So as we did in the last section, in factoring a simple trinomial, we look at the last term, which is negative 25, and list all the factors of negative 25, and find the pair that add up to the middle term. So negative 25 can be written as negative 5 times positive 5, and when you add negative 5 and positive 5 together, you get 0. So the factors of n squared minus 25 are n plus 5 and n minus 5. Now when we include that with our original greatest common factor of 2, this polynomial can be written in factored form as 2 times the quantity n plus 5 times the quantity n minus 5. And so what this slide is indicating here is that whenever you have a perfect square minus a perfect square, the difference of squares can be factored in the form of x plus y times x minus y. Let's factor this polynomial. There is no greatest common factor in 9 and 16, so if we can recognize that this is in the form of a squared minus b squared, that can be factored into a plus b and a minus b. Well, the a in this case would be the quantity that when you square it, it results in 9g squared. So that quantity is 3g to the second power. And 16 is a perfect square that can be written as 4 to the second power. So it is in this form of a squared minus b squared. In using this model equation, whenever you have a difference of squares, the factors are a plus b and a minus b. But instead of a, we're going to use 3g, and instead of b, we have minus 4. So one factor is 3g plus 4, and the other factor is 3g minus 4. Again, we can check our answer here. The way we check is by using FOIL. Our first 3g times 3g is 9g squared. 3g times negative 4, the outer, is minus 12g. The inner, 4 times 3g, is a plus 12g. And then the last, then positive 4 times negative 4 is minus 16. Now notice in this case, the outer and the inner are opposites, so this simplifies to 9g squared minus 16. So that's the key in doing these. If you recognize it as a difference of two squares, then you can determine the factors of a plus b times a minus b. Perfect square trinomials are also ones that if you recognize the pattern, you can determine the factors. Here we have 9g squared minus 42g plus 49. If you recognize the trinomial where the first term is a perfect square, the second term needs to be minus 2xy, which we'll get to in a second. The last term is a perfect square. So if the middle term is minus 2 times the first term and second term before you square them, you can determine the factors. Well, in this case, our first term can be written as 3g, the entire quantity squared, and the last term, 49, can be written as 7, the quantity squared. If the middle term is twice the first and last term before they're squared, 2xy, then we can recognize this as a perfect square trinomial. So if this is minus 2 times your first term before it's squared is 3g, your last term before it's squared is 7. If negative 42g is equivalent to negative 2 times 3g times 7, which it is, we can recognize this as a perfect square trinomial. So the way we factor this is that it needs to be in the form of x minus y, the entire quantity squared. So in this case, we have 3g minus 7, the entire quantity squared. The way you can check your answer would be to use the FOIL process. When you have an entire binomial squared, you can write this as 3g minus 7 times 3g minus 7, and using the first, outer, inner, and last, you can check 3g times 3g is 9g squared. The outer, 3g times minus 7, is minus 21g. The inner is negative 7 times 3g, another minus 21g, and the last term is plus 49. When you combine those middle terms, you get 9g squared minus 42g plus 49, which is what we started off with. So this will be our trinomial in factored form. So in this section, we're looking for these special terms that can be factored. All right, take a look at this example. We want to factor this polynomial. It looks like it's in the form of a perfect square trinomial, and the perfect square trinomials can be written as a squared plus 2ab plus b squared. If that's the case, this can be factored into a plus b, the entire quantity squared. So if you recognize a first term is a perfect square, 25x squared, you can write it as 5x, the entire quantity squared. 64y squared is a perfect square, which can be written as 8y squared. And if that middle term is 2 times 5x times 8y, then we can say that it follows this pattern, 2ab. However, if we check this, we have 2 times 5x times 8y. 2 times 5 is 10. 10x times 8y is 80xy. The middle term here does not follow this pattern of plus 2ab. So in this case, the trinomial cannot be factored using this special perfect square trinomial. The difference of cubes is another one of those common patterns of polynomials that can be factored using a model equation or model formula. If we can recognize that the polynomial is written as a perfect cube minus a perfect cube, then we can use this model formula to pattern the factoring. So a to the third power obviously is a perfect cube, and you can write it as a to the third power. And 125 is also a perfect cube, and that can be written as 5 to the third power. So we're going to use this model equation here as x cubed using a cubed and y cubed using 5 cubed, and be able to find the factors. For the difference of two cubes and for the sum of two cubes, the factors are always in the form of a binomial times a trinomial. So the first factor, the binomial, is found by taking x minus y. In this case, so it's going to be a minus 5. The second factor, the trinomial factor, is found by taking x squared. So in our example, it'll be a squared plus xy. That's going to be plus a times 5 or plus 5a. And then the last term in the trinomial factor is y squared. And in our case, that's going to be plus 25. So this is the factored form of the difference of cubes. You can check this using the distributive property. It has a few more steps than the FOIL, but you're going to multiply a times each of the terms in the trinomial and b times each of the term in the trinomial and combine like terms. Let's do that. If you multiply the first term, a times a squared, you get a to the third power. A times 5a is plus 5a squared. A times 25 is plus 25a. And then multiply each of those terms by negative 5. Negative 5 times a squared is minus 5a squared. Negative 5 times plus 5a is minus 25a. And negative 5 times a positive 25 is minus 125. Notice that there are like terms here. The plus 5a squared and the minus 5a squared are opposites. Those are going to cancel out. The plus 25a and the minus 25a are also opposites. They're going to cancel out. So the resulting polynomial, the simplified polynomial, can be written as a cubed minus 125. This is one of the special factoring techniques when you recognize the polynomial as a difference of two cubes. The two factors, one will be a binomial and the other will be a trinomial. So this would be our answer in factored form, and this is our check step. Factor each polynomial. Again, we're looking at the polynomial to determine if it follows one of those special factoring formulas. In this case, it does look like a perfect cube, a difference of two cubes. 8g to the third can be written as 2g, the entire quantity to the third, and h to the third. We do have a difference of two cubes. We can write this as a binomial factor and a trinomial factor. The first factor in the model is x minus y, so in our example, 2g minus h is the first factor. The second trinomial factor is written in the form of x squared. In our case, 2g is our x, so that's going to be squared to get 4g squared plus x times y, 2g times h, and the last term in the trinomial factor is y squared, and that'll be h to the second power. This is our answer written in factored form. You can obviously check this using the distributive property to make sure you end up with the original problem. Another example here, factor the polynomial, and we're recognizing that the polynomial is in the form of a difference of two cubes. 64 can be written as a perfect cube, 4 to the third power, so we can write this as 4m quantity to the third power. 27 is a perfect cube as well, so we can write this as 3n to the third power. By recognizing that we have a difference of two cubes, we use the special factoring formula, the first factor being x minus y in the model. So in our example, it's 4m minus 3n. The trinomial factor is x squared, and that's going to be 16m squared plus xy. 4m times 3n is 12mn, and the last term in the trinomial factor is plus y squared. So for us, it's going to be 9n squared. So our final answer written in factored form is the binomial factor of 4m minus 3n and the trinomial factor of 16m squared plus 12mn plus 9n squared. The sum of cubes is also one of those that you can recognize and apply the formula. For the sum of cubes, you have x cubed plus y cubed, starting with a binomial factor of x plus y and the trinomial factor of x squared minus xy plus y squared. This example A follows that form, where n cubed, that's your first term, and 8 is a perfect cube as well, and that's 2 cubed. So instead of x and y, we have n and 2. Our factored form for this polynomial is x plus y in the model, so in our example, we have n plus 2. The second factor is the trinomial x squared, which for us is n squared, minus x times y, minus n times 2, minus 2n, and the last term, plus y squared, will be plus 4. This is our answer in factored form. We can check this using the distributive property. We're going to multiply n times all of those terms to get n times n squared is n to the third, n times minus 2n is minus 2n squared, n times plus 4 is plus 4n. Now if we multiply each of those terms in the trinomial by 2, we get 3 more terms, and we get 2 times n squared is plus 2n squared, 2 times negative 2n is minus 4n, and 2 times 4 is a positive 8. We do have like terms here. The minus 2n squared and the plus 2n squared are opposites, as well as the plus 4n and the minus 4n are opposites. This simplifies to n to the third plus 8. That's what we started off with. In factored form, we get n plus 2 times the quantity n squared minus 2n plus 4. All right, a note on the signs for those model formulas for the difference of cubes and sum of cubes. The sign of the second term in the binomial factor of a sum or difference of cubes is always the same as the sign in the original polynomial. The original polynomial here, it has a minus sign, so the first binomial factor has the same sign. Sum of cubes, the original polynomial has a plus sign, so the first binomial factor also has a plus sign. In the trinomial factor, the first and last terms are always positive. Okay, so the first term is always positive, the last term is always positive, but the middle term is always the opposite of the sign of the second term in the binomial factor. If it's the opposite term, so if we have this is a minus, this is going to be the opposite as a plus. This is a plus, this is going to be a minus. It's a good idea to write down those basic formulas for the sum of cubes, difference of cubes, as well as the difference of squares. Keep those on flashcards handy and refer to them often until you're able to memorize those without having to look at the card. Let's factor this polynomial 64v to the third plus 27g to the third. Recall that x cubed plus y cubed, the sum of two cubes, can be factored as a binomial and a trinomial. We want to be able to write 64v to the third as a perfect cube. 64 can be written as 4 to the third and v, so this quantity can be expressed as 4v to the third power. 27 is a perfect cube that can be written as 3 to the third power. So group that with the g so that your entire quantity 3g is raised to the third power. The first binomial factor is going to have the same sign. We have the first term of 4v plus 3g as the binomial factor. The second trinomial factor is going to square the first term. 4v squared is 16v squared minus x times y, or minus 4v times 3g minus 12vg, and then the last term is plus y squared, in this case 9g squared. Let's look at this polynomial. 2k to the third plus 250. Now 2 is not a perfect cube and 250 is not a perfect cube, but there is a greatest common factor that you can factor out of both before applying the formula for the sum of cubes. The greatest common factor, the number that goes into both of those terms, is 2. So let's factor out the 2 first. When you factor out the 2, you get k to the third plus 250 divided by 2 is 125. 125 is a perfect cube, so this problem can be written as k to the third plus 5 to the third. And since the k to the third plus 5 to the third fits in this model formula here, we can further factor that into the binomial and trinomial, keeping that 2 out in front. So our binomial factor is going to be x plus y, or k plus 5. The trinomial factor is x squared, that's k squared, minus k times 5, which is minus 5k, and the last term squared plus 5 squared is plus 25. This would be our final answer expressed in factored form. To check this, you can distribute the 2 and then distribute using the polynomial multiplication. All right, factoring summary. In this section, we looked at factoring the difference of squares, recognizing some polynomials are written as x squared minus y squared, and we can find the two factors as x plus y and x minus y. We also looked at perfect square trinomials. If you have a trinomial and the first term is squared, a perfect square, and the last term is a perfect square, and the middle term is a combination of those, then it can be factored as a perfect square trinomial. The same thing with the minus here. We looked at examples of difference of cubes. If we can recognize the pattern where we have a perfect cube minus a perfect cube, the factor is a binomial and a trinomial. The sum of cubes, if it's a perfect cube plus a perfect cube, we can factor it into, again, a binomial and a trinomial. Write those formulas down, look at them often until you get to memorize those. Those will come in handy.